Swayam Prabha. Digital India. Educated India.
So, as we were discussing, parameters of aircraft are going to play a role in changing the eigenvalues, location of the eigenvalues on the complex plane, right. So, we were in the last class discussing the effect of changing the CG, we are moving it aft, so that the starting margin is going down, and we want to see the effect of that on the location of the eigenvalues. The effect of stability derivatives on the longitudinal modes, right. What we want to look at is how the short period and the Fugite mode eigenvalues are moving when we are changing something. So, the variation in the direction of the arrow is CG is moving up. So, to start with, my CG is at some place, and then I start moving the CG backward, right, towards the neutral point. So, static margin is going to decrease, right. So, let us see what happens to the Fugite mode eigenvalues and the short period mode eigenvalues. So, we are changing CM alpha, isn't it? So, when you are changing CM alpha, what is going to change? The short period frequency, right. We got an approximate formula for this as this was for the case when we are looking only at the constraint pitching motion. So, and plus something, right, plus something that is coming from the Z alpha term. So, we want to So, effect of changing CM alpha is going to be on the short period frequency, right, and what is happening here? Exactly the same. So, damping is constant because we are at the same location on the real axis, right, and the roots are moving in the direction of the arrow vertically. So, the frequency is decreasing, right, and once it reaches here, it splits like thus. Let us look at what is happening to the phugoid mode. Now, you will not expect the phugoid eigenvalues to change, right, because of Cm alpha term, but changing Cg is also going to change something else, right, or in other words, now as I said, short period motion and the phugoid motion are coupled. So, the short period mode is going to have an effect on the phugoid mode. That is what we discussed yesterday. So, phugoid mode eigenvalues are also going to move when we change the Cg. Okay. So, you can go on actually doing this, no, change some parameter, see the effect of that on the location of the eigenvalues. This is called root locus. Okay. When you change parameter of the system and look at how the roots are moving, the trajectory of the roots in the complex plane is known as root locus. So, let us look at one more effect of one more parameter on these two eigenvalues. Remember, there are things which you can change, right, and there are things which you cannot. So, two of the things that are kind of still in the hand of the designer. If you have a tail, now wing sizing will depend upon the performance requirements, right. Tail sizing is usually depending upon the stability requirements. So, here I am showing you the effect of those parameters on these two eigenvalues which are still under control, right. You can still design your horizontal tail area, you can make it bigger or smaller, and you can change the CG definitely, because you can have dead weight inside your aircraft which can be moved to change the CG. And you also would want to look at the location of these eigenvalues when passengers are moving on the aircraft. So, this plot gives you that information. Let us look at the horizontal tail area effect of changing that on the longitudinal mode eigenvalues. What is tail area going to do? If you increase the tail area, it is going to, no, it appears somewhere in the expression for Cm alpha. Remember, when we added tail, we increased Cm alpha. So, tail is also, this horizontal tail is also known as stabilizer, right. So, you are adding to the Cm alpha. What else? Remember, we also defined the damping term with respect to the tail coming from the pitch rate, right. Yeah. What is it? Okay, so we are coming to that. So it's going to so frequency is going to become what? Higher, and damping it will also be higher. So it's going to move in this direction. But phugoid effect of that is also to change the phugoid frequency, right. So phugoid frequency becomes large and the time period becomes small. No, usually don't worry about the phugoid if you have a really good pilot sitting inside the aircraft, no, because he can take care of that. He can apply corrective actions to control the aircraft in phugoid, because the time period involved is very large, right. But if such a thing happens, then you are going to lose that advantage. Frequency is going up, so time period is going to be smaller, right. So the problem associated are these. If the damping is low in short period, then controlling the motion is going to be difficult, right. Low damping in any motion is going to be difficult to control, right. Phugoid, no, this is related to the pitching motion. Short period mode eigenvalues are related to the pitching motion of the aircraft. So if it is not damping fast, right, then this pitching motion is going to last longer, and I am sure you are not going to like it when you are sitting in such an aircraft, right, which is doing this and it is taking longer to settle. Phugoid is a long period motion. Even though a pilot can control it, it can become really tiring for the pilot, right. So there we actually start talking about pilot comfort with the aircraft, right, and that is related to the flying quality of the aircraft, okay, flying or handling. So there is a scale, the scale Cooper Harper scale, on a scale of 1 to 10. Now it tells you what kind of quality your aircraft is having, okay. So this on 1 to 10 scale, if the rating is 1, then your aircraft is excellent, okay, in terms of satisfying the pilot in terms of all other requirements, okay. If it is 10, then you better go back and change something in your design, or maybe you change a design control system which can add to the flying and handling qualities. So this rating 1 means excellent flying, and 10 is when it is really bad and you recommend mandatory improvement. Actually 7 to 10 is objectionable and it relates to major deficiencies. And this rating is based on 3 different criteria. So, these criteria are depending upon pilot's input, how much pilot workload goes up or how comfortable pilot feels operating the airplane. So, there are 3 levels which relate to pilot workload. So, level 1 is if your aircraft falls in this category level 1 or this level, because category is another thing here, then you have adequate flying qualities. No, pilot feels really good about flying this aircraft. So, this airplane can be flown comfortably by the pilot, but only at the cost of increased pilot workload. Level 3 is airplane can be controlled and flown safe, but pilot workload is excessive. It also depends upon what category of aircraft you are talking about. So, category is based upon the phase of flight, okay, maneuvering phase of flight. Category A and B are related to non-terminal phase of flight. So, these 2 categories are related to what does this mean? So, you are not talking about flights which are related to ending the flight or beginning of the flight. So, non-terminal phases of flight. So, it is about maneuvering, right. So, category 1 is related to rapid maneuvering, high performance aircraft, the maneuvers. Category B is related to gradual maneuvers. And these maneuvers are it can be cruise, turn, loiter and so on. Category C is related to the the terminal flight phases, and in this case takeoff, climb, approach to land. All right. Now, what kind of aircraft we are talking about? That is not clear, isn't it? So far we did not talk about the type of aircraft. So, you have 4 classes of airplanes. So, in class 1, small light. So, class 1 belongs to this small light airplanes. Class 2 is medium weight, you are going to see all kind of airplanes, all variants. For example, if you are flying cross Atlantic, you are flying in a Boeing 747, right, capacity 400 plus, right. In India, within the country you are flying in a 100 120 seater. If you are flying from let us say Delhi to Kanpur, it's a short distance, you are going to see some airplane with only 20 passengers capacity, seating capacity, right. So, you have different class of airplanes. Now, other than combat or non-combat aircraft, you have these classes also. So, class 4 is the class belonging to the combat fighter airplanes. Now, how do I define this rating in terms of level, category and class of airplanes? That is what we should talk about, and the only thing that I worry about is the eigenvalue, right, because that is what is going to tell me about the aircraft behavior, about perturbed behavior about an equilibrium state, right. So, let us look at the flying and handling qualities, keeping these three types in mind. Let us talk about longitudinal and these qualities I want to define in terms of the damping and frequency characteristic of the longitudinal modes. So, you have good flying quality in phugoid mode under these levels, and the damping ratio is level 1, if it is greater than 0.04, then you have good phugoid characteristics, right. Level 2, the damping should be positive. Level 3, it is defined in terms of the time period, okay, and this should be greater than 55 seconds, right. So, even if you have a divergent phugoid mode, that is the that is unstable phugoid mode, right, then you should have the time period of doubling the amplitude, the time of doubling the amplitude, right, should be more than 55 seconds. And this is true for all category of flight phases and all class of airplanes, right. Here the quality is depending upon both level and the category of airplanes or category of flight phases. these numbers are standardized, okay. So you will find these numbers same in all the textbooks, they are not going to be different. What this means is it's not given, okay, for this level. Okay, so with this we conclude our longitudinal perturbed dynamics. Let us look at perturbed lateral motions now. Okay. So what is happening is we are again considering the same equilibrium flying condition, and now we are not bothered about what is happening in the longitudinal plane, right. Now we want to look at dynamics in the non longitudinal planes, right. So aircraft is flying this cruise condition, right, and gust will hit the aircraft as usual, and you want to look at the perturbed motion. So motion is going to be in roll, right, and yaw, side slip, right, and the bank is associated with the roll. So the variable of interest here are delta beta, delta p, delta phi, and delta r, right. So my state variable vector, the perturbed state variable vector is now consisting of these 4 variables, and the control vector is consisting of perturbation in aileron and perturbation in rudder, right. So we are looking at longitudinal and non longitudinal dynamics as completely decoupled, and that will happen only in this particular flying condition. If you are talking about let us say level turn, then it may not be decoupled, right. Okay. The dynamic modes perturbed, right, dynamic modes are related to the perturbed motion of aircraft from the equilibrium state. So dynamic modes here are Dutch roll, second is roll. Now Dutch roll is different from roll, okay. It appears to be rolling but it is not actually rolling, that is why this name. And spiral. If you look at the location of the eigenvalues corresponding to these modes in the complex plane, typically they are located like this. Okay, so pair of complex conjugate eigenvalue and two real eigenvalues, right. Many times this mode, which is called spiral mode eigenvalue, can be lying also on the other side, right. So other side, if it is lying, it's like a divergent mode, right. So if it is lying on this side, then you have a motion called spiral divergent motion. This pair of complex conjugate eigenvalues is related to the Dutch roll motion, okay. And this eigenvalue is related to the roll mode. So you see here that this eigenvalue is actually lying quite far from these three, right. So we can now kind of assume that this particular motion is decoupled from the rest, right, and based on that we can now make some approximations. Okay. So before we go into doing that, let us try to understand what a designer would be worrying about, okay, when he is talking about lateral motions. What is exactly in his mind? A designer will be worried about the divergent motion, right, unstable motions of aircraft. He has to ensure that aircraft is stable, right, to start with. Now if it is unstable, how unstable it is, right. So these are three modes of motion in lateral directional dynamics which the designer has to keep in mind. Okay. Let us try to understand what these motions are. So you are flying, you are still flying a cruise condition, and now you have a gust from side. So there is a change in side slip, and that will change, that will result into the perturbed motion of the aircraft. So you are flying in this, actually on this line, at some altitude you are flying along this line with velocity vector in this direction, right, and flying level. So altitude is fixed, wings are level, right. So let us see what happens with respect to some of the parameters that we have already seen earlier. If the aircraft is having low Cn beta, okay. So small Cn beta, what effect that will have on the aircraft motion. So a perturbation is introduced, the Cn beta will not be enough to kill that delta beta, right. So aircraft will start going on a curved path which is like this, and the beta will keep on increasing, okay. That delta beta will keep on growing, and finally your aircraft will be flying like this, right. So the beta has grown. Ideally it should have killed the beta. If it had enough Cn beta, it should have killed the beta, but the velocity vector is in this direction now and aircraft is looking somewhere else. So that means there is a beta introduced, right. So there is a non-zero side slip which can be large if you keep on going, if you do not correct it in time, and this is related to, so this motion is called directional divergence, okay. So there is another situation when you have enough Cn beta but you have low Cl beta, right. In that case what happens is aircraft still follows a curved path, but it is able to kill that beta because it has large stiffness in yaw, right. So now it will follow the velocity vector, right. So beta is 0 all the time, but because of the Cl beta which is low is going to give rise to a rolling motion, right. So slowly the aircraft is actually is killing the beta, so it is moving like this but it is also turning, right. And because the bank is introduced now, you will have a left component which will be lower than the weight, so it will also start going down, right. So steeper bank and it is going down, so it is going into a spiraling motion about a vertical axis. So this is called the spiral divergence, all right. This Dutch roll motion is predominant in beta and R, okay. Actually there is not much roll involved, it looks like, it appears that the aircraft is rolling but it is actually not rolling. So what is happening here is look at this, so you are yawing, right. So you have a yaw rate R which is non-zero, you are yawing and you are also side slipping. No, these two are two different things. Yawing is a pure yawing is rotation about the z axis, right. Beta is the angle that is making with the velocity vector, the nose of the aircraft, the angle that it makes with the velocity vector is the side slip angle. So it will do this, but go like this, right. So it is doing this in one direction, in the other direction is this, and going like this. So it is like something like this, right. So it appears that because of that motion it appears that it is rolling. Look at this, if I can put it correctly. So maybe it needs a little practice, something like this. So it looks like it's rolling, okay, but it's not really rolling, but there is some amount, very little amount of roll involved.
That's not supposed to be a closed loop thing.
Yeah, this is what actually we observe in flight. So it looks like it's the wing tip of the aircraft is making some curve, closed curve, which we observed this time. So that is where when you now make assumptions that it only involves beta and r, and then arrive at the approximate formula, you will find that that formula is not really correct. So there is some amount of roll involved, okay, and that we will discuss in the next class. So we can stop.